So yes, indeed, I'll be talking about the basically my attempt to ascertain the ontology of relativistic quantum field theory in recent years. Like any of our thoughts, this involves balancing a number of concerns, especially from philosophy as well as physics. I'm trying to do this, although I publish usually this work in physics journals. It definitely will have a philosophical side to it. So just some background thoughts. I apologize for the way it's a little bit difficult to read on the screen, but a couple of quotes from Einstein and Feynman that are good. It's a sort of background thing to meditate on before I begin with the talk. First of all, pretty obvious thing by Einstein, but Einstein can say obvious things and everyone pays attention. So physics should be as simple as possible, but not simpler. This is always a good thing to keep in mind as one does physics. And of course, when Einstein did physics, it wasn't just physics. His starting points were not, let's take existing theory and then just see what we can do with it. It was really, let me think about what's happening in the world and think about this in as clear and simple possible way, and then see what this brings in. So that will have something to do with the methodology that ends up being applied here. And then also the always provocative American Richard Feynman. If all mathematics were to disappear, physics would be set back exactly 1 week. Obviously, hyperbole, but the reason I find this an interesting thing to mention here is that it's easy to be led by the nose by technicalities in mathematics. If you're trying to do philosophy of physics, mathematics is very important. Sometimes the thing which is keeping you in touch with what you have to be in touch with, but you should also be aware that maybe just like parents, you don't want to hold on too tightly. At some point, you have to leave the mathematics a little bit and reconsider that perhaps your family could be more than just your parents. Like just to keep these things in mind before that. So I think it's good to have a very big, broad context in the discussion of ultimate existence. So if we just sort of think about how people have searched for the ultimate physical ontology, in other words, what exists and how it's, the things that exist relate to each other. We like to think about what is involved in doing that. And this is, of course, a little bit on the philosophical side. But you're going to have to think about the world as being structured in some way in order to have order. So we think again about Einstein, his whole basis of thinking about physics was trying to have an actual context in which one could think logically about physical behavior. If you really think about why he was a local realist, it all had to do with how he's going to be able to structure the world to do physics. And certain things he thought were essential. These are debatable. This is a typical thing that happens. So in history, you find people talking about substances and objects. And of course, one of the key essences in philosophy of substance is that you're actually having a certain objective character. So substances have been, since Aristotle, something that people have had in mind when they try to do some investigation of the physical world. More modern thing is an event, something happens. This also gives you an alternative way of structuring the world. You may think that the world is fundamentally based on events. So in the context of quantum field theory, for example, Rudolf Hahn was somebody who thought events were the primary thing, even prior to space and time. I won't go so far as that today, but that's something to keep in mind. Then, of course, the properties of objects. We spend most of our time when we do physics thinking about how the properties of objects relate to their behavior or even their behavior as properties. Okay, but then you'd like to have conditions that you impose on the world that start to move you in the direction of principles. And for example, independence of things, which relates to objectivity, invariance. Okay, so what things matter and what things don't matter to my structuring the world. And also, can I compose and decompose things, which has to do with, I would say, probably the strongest subconscious, perhaps, or often subconscious idea related to the atomist philosophy of trying to break down things into smaller pieces and think about how things are composed, the reality of things. So, of course, if you go back again to the ancient Greeks, you go back to Aristotle, 4 elements. Sometimes we think of them as chemical, but of course, chemistry and physics was not very strong then. If you think about distinctions of the chemical elements that Aristotle and people at his time were thinking about, it basically had to do with their physical behavior. What was the nature of their motion? Right, and also how things were composed. And as we went forward, we started to realize that we can, in physics, break things down into smaller elements. And again, if you're thinking about the broad context of atoms, you'd really like to get to the point of finding some level at which you could think of the world as structured in. And this, quite happily happened in the case of chemistry, reducing to physics to some extent. And of course, I wouldn't emphasize that because it's really not the case. Reductionism is very difficult to carry through, but it's obviously been very successful. And again, referring to Feynman emphasized in his thinking that atomism was, he thought atomism was the most important philosophy of thinking, or the most important methodology for thinking about how to do physics. And I didn't realize that until recently. I was quite surprised to hear that from him, but it's true. In addition to his general disrespect for rules of mathematics, negative probabilities and so on, no problem, right? Okay, so I noticed that one of the other, or two, perhaps, or even more than two people are going to be talking later on using the notion of experimental metaphysics. And really, when you start to mix philosophy and physics together and then have anything to do with observation, there's a sense in which you're doing what's called experimental metaphysics. So if you really try to think about this whole process of getting to the ontological structure of the world, you really would, in doing physics as an empirical science, want to be doing some form of experimental metaphysics. So I'm going to start off by talking about a little bit of the history of this concept, because I think it's interesting and not so well known. And it's certainly something more general than reductionism, something having more freedom of thought when it comes to trying to structure the world, not just, oh, we must find the atoms, and once we find the atoms and we figure out how they behave, we're all set. Of course, that's something we're realizing is fairly absurd, but again, very important in history. So the first mention of the actual term experimental metaphysics was actually regarding quantum mechanics, and I think the reason for that is that in our collective scientific memory, this is the strongest thing. Of course, working foundations of quantum theory. This is what we're being pummeled over the head with constantly. We have to reconsider our ontology or our metaphysics, or somehow what is the nature of reality since the quantum revolution. And so Shimoni in '84 published this statement, and I'm quite sure that in Boston at the time, at MIT, where I was just before this time, people were talking about this sort of thing. I think this is more like a phrase that he coined, but coining the phrases is very important. So let me just read it. Well, the whole vast body of experimental results which have probed and confirmed quantum mechanics, I should say this could be any type of physics really, can in fact be regarded as contributions to experimental metaphysics. And the mathematical analysis of the structure of quantum mechanics has made explicit its metaphysical content. And of course, what he really means there is probably what can you do with Hilbert space and how you can structure Hilbert space. And of course, entanglement would be something which would challenge the reductionist picture quite clearly. And so that's the sort of general context of that. But really, this is not something that Shimoni came up with. It's something that was in the air. And I'm actually increasingly, as time goes on, impressed by Max Born and the depths of his thought. So one finds in this nice collection of essays, and I'm not sure it was all written in the 50s by Born, published in '56. There's I would say, a more definitional rather than referential use of the concept of experimental metaphysics in one of these pieces. Born says, experience leads us again to an alteration of metaphysical foundations. Physics free from metaphysical hypotheses is impossible, or hypothesis. So that's the importance and significance of physics and philosophy being done, foundations of physics right there. These assumptions have to be distilled out of physics itself. So this is again because it's an experimental science which has hypotheses which we gain confidence in, and then we can actually bring them to a deeper level if they pass muster philosophically, right? And continuously adapt into the actual empirical situation. And so this is what I found myself doing when I tried to think about what is the ontology of quantum field theory. So I was quite happy to find this quotation, and I'm sure that Albany would not object in any way whatsoever to saying that there was some precedent. In fact, one always has to look back to the history in the Shimoni school of thinking and not take too much credit for things which other people have brought to the table, as Newton did with the shoulders of giants. So I do have some criticisms of the way that ontology has been dealt with over this now almost 100-year, I would say definitely 100-year period, that people have been asking the question of what quantum theory does to our thinking about the world, or taking into account what that makes us do. But I would say that in the high era of experimental metaphysics, from Bell's theorem onward, there's been a very strong focus on formalism, theoretical formalism. And part of this maybe has to do with the way that people are doing, at least in the United States, the way people were doing philosophy at the time.
Excuse me, Greg. Sorry to interrupt. I think there's almost like cultural question now, because there are these two cultures. I think in physics it's much more usual to ask questions during the talk. In philosophy, it's usually afterwards. We haven't talked about how we want to do this at the workshop, and I'm totally open to both. And maybe every speaker should indicate at the beginning of the talk whether they want to take questions during the talk or wait until the end. Sorry, we haven't done this in the beginning because we had one question. So I'm not sure if you want to take it right now or at the end of the talk.
Well, I'm pretty open to having questions during the talk. It's just that if they require long answers, then maybe I would hold off. It depends on how the flow of things goes. So, but for sure, if I'm not making sense to you, please do ask a quick question. If something's really undefined, I would be very happy to respond. I didn't see who was asking.
Well, I will add this point, I just ask it. So thank you, and I really like the phrase experimental metaphysics too, but I feel that there's a certain confusion or like not very well defined kind of a notion of metaphysics. Because I think there's physicists tend to understand it as whatever is beyond physics. Whereas in philosophy, right, it's kind of a subject per se, which started with the book of Aristotle.
Right, so that's what I'm talking about when I say metaphysics. But I realize it's a bit absurd to say experimental metaphysics as a phrase, right? So, and that's of course what you want to do. You want to have a phrase which makes you think. I'm always very well aware as a physicist and philosopher, actually was the president of the Philosophy of Science Association of the United States. When he came up with this, he realized that it had a kind of paradoxical quality. So I think the idea is that one should be empiricistic in a certain way. So we can talk more about this later, but I certainly do think metaphysics in the deeper sense. And this is how this is being used in, say, the 20th century. It was used, and why people like to use it. Not many other people will use it, and we can see how they use it as well, because I've given more or less my definition of it. So my criticism of how things have been going in the foundations of quantum mechanics, anyway, has been, I think, a hyper focus on theoretical formalism. But if you have this formalism, this is the thing which you need to be addressing. And of course, if you're doing the interpretation of quantum mechanics, what does it mean to interpret quantum mechanics? Well, if you've got a formalism, what does it mean? What's being referred to? What is the meaning when you produce some kind of statement? What are you actually saying? And of course, this can become very deep very quickly. However, there's a threat, and I think this is a threat in quantum field theory, of simply attempting to read off formalism. I will show, or at least refer to, some problems with trying to do that in quantum field theory. Simply reading off the formalism and saying, well, here's the formalism, and so I've got a quantum state, so therefore I'm talking about this and that. Or if I have a Hilbert space vector, therefore I have a system. System is actually very much more a vague concept than people really take into account. It's actually quite shocking as a student. You may at some point ask yourself, what is a system? And generally speaking, it's something you can draw a line around in the universe. Well, okay, that's pretty vacuous, right? On the other hand, that's what we do. So that's interesting. So my use of this concept of experimental metaphysics, in other words, reconsidering how physics might relate to metaphysics, let's say, maybe is the best way of putting that, is to find essential properties in objects from observation, so being empiricistic in that sense. Then analyzing the mathematics of theories that you might have for possible objects and structures without automatically going to look and examine the procedures that are carried out by physicists, assuming they, of course, are quite capable of doing what needs to be done philosophically, because I think that that's, generally speaking, not the case as you might see in the slide to come. But of course, you want to ultimately try to adapt your ontology to the experience according to principles. So you want to stay with respecting broad principles, but not being led too much by the formalism or modeling that people are doing in order to make physical progress. So, if we look at a couple of realisms, and I do identify myself as a realist, one can have realism about various things in philosophy of science. And scientific realism about theories, again, on this general idea of emphasizing theory, which I think Kuhn's thinking about scientific revolutions has had a big impact on. Scientific theories are, according to a nice definition by Putnam, who is one of the strongest advocates of early scientific realism, which has been seen to be a little bit simplistic. But the general idea is that scientific theories are at least partially true accounts of what's happening in the world. And that's the best explanation for their success. And that's the reason one should have confidence in the existence of the reference of physics, for example, or any other science. Now, Michael Dixon, who actually I think has recently been the head of the Philosophy of Science Association of America, had the following statement trying to understand how physicists relate to this question of realism without actually being philosophically conscious in most cases, right? And his conversation of the way that physicists tend to think about what's real is the following. An experiment reveals, at least somewhat directly, a physical entity corresponding to the theoretical elements in question. In other words, if you are thinking about a theory, you attempt to do an experiment, you do an experiment, and if you find that your experiments reveal behavior that accords with theory, then you can assume that this thing is, or that's the assumption that the thing you're talking about is physically real. And moreover, and this is the more problematic part, is more or less the way the theory says. Why would that be problematic? Well, our theories change, right? That's the whole point of the scientific revolutions and the strange result of the historical analysis of Kuhn of what's happened in the history of science and astronomy and problem theory. I prefer to think about ontology in the context of a progressive ontological realism, which I would phrase as saying, in the following statement, the entities that continue to be referred to by science are real, and comprehensive, accurate notions of them are developed as science progresses. And I think someone will be giving a talk later in this meeting about the impact of technology on these matters. And of course, that's what allows us to look more broadly with physics in recent times, of course, into the microscopic and submicroscopic realms, which is the quantum mechanics in the first place. So, a quick overview, because I never know how far I'm going to be able to get in the amount of time that I'm given. I'm talking about a topic like this, but there are some ontological questions in the philosophy of physics that I will try to address in this talk to various extents. And I've got my brief answers here for you, so you have a sense of where I'm going with this. First of all, what are the fundamental objects of quantum field theory? In other words, how do we start structuring? What's our ontology? And I argue for ontology of both fields and particles. This is a little bit unusual. I think people have been in the philosophy of physics trying really to argue, philosophy of quantum field theory, argue that for fundamentalisms, either they're just fields or they're just particles. And if there are particles and fields, that those particles should be reduced to fields, and so really it's a matter of just quantum field theory. As you might imagine, looking at the title of the theory, it's not called quantum field particles or theory of fields and particles usually, although the standard model is what standard model of particles and fields. So that's one reason why I would say both. So then, of course, what is the question of, what is the relationship between particles and fields? And this is a subtle technical question. I'm going to give a sense of what that relationship is, and I would say that particles supervene on fields, and this is sort of a more go-to concept in the philosophy of mind. What's the relationship between mind and neurology, right? So mind supervenes on mental things or mental states supervene on neurological states to give you a sense of where I might be going with that. But of course, I want to stay in a very well-defined physical context when I do that. There's also the question of virtual particles. And this is a very interesting question because these are one of the most quickly rejected, but often very practically used notions in energy physics, virtual particles. So I'm going to try to argue that virtual particles exist not because I want to do that, but because I think if you take the whole context from the philosophy and physics side and looking at quantum field theory, you'd be compelled to exist, or at least that there's a certain degree of virtuality if you want to go there on particles, simply because the particles that we talk about in quantum field theory standardly are things which are defined in an ideal situation which doesn't really hold. So it's a little bit like the ding on Z, if you like, of physics. So this if you again return to the broad sweep of history and the impact of atomism, if you think about how important corpuscles, which are really pieces are at the time, perhaps the atoms, but the parts, the fundamental parts in the history of classical physics, one could say that one would have, with the success of understanding the structure of matter and statistical physics eventually and so on, that there's an ontology of classical physics, which is one in which corpuscles, particles are basic things, and they have certain properties, for example, being localized, being independent of one another, which has its own statistical characteristics. What does it mean to be localized, let's say spatially delimited? And you can ask yourself various questions about Cartesian views of matter and so on. And there are many different ways of spelling this out, but that's still the broad context of something that's going on. And of course, re-identifiability, and I'm not talking about object independence in any kind of sense of Piaget or whatever, but being able to say, I've got this particle, later on I see it, the same particle. That's much more problematic when we move to quantum, right? The model that's generally used for elementary particles is actually quantum in our contemporary physics and quantum field theory. And one finds, and of course the various modes of analysis are available, but these particles are not really localizable, certainly not in the sense, we can talk about the technicalities that are related to that, but they're not localizable, certainly in the sense of classical physics. But there are even arguments, for example, Mountain's theorem, which indicate that it's really not possible to localize particle at all. Again, you have to take on certain assumptions to do that, but certainly localizability is an issue. Also, independence is not something which is really obeyed by quantum particles. You've got your fermions and bosons, and of course, they are not independent of one another. In general, if you want to have them identified as independent things, that's usually just a momentary thing, and that's also something itself which is questionable. And certainly, they're not always re-identifiable. Conditions in which you could re-identify a particle are quite extreme. So, it's really, if you think, for people who are familiar with quantum mechanics, in a very basic quantum mechanics, the idea that if you just immediately measure something after you've measured it, it has a certain objectivity and certain characteristics which you can immediately re-identify. But then, of course, you've got to be staring at this thing all the time. And depending on how much confidence you have in zero effect, there may be nothing happening whatsoever. There's no real physics there. So, okay. So, but the real problem that one finds in trying to do what I'm trying to do anyway is that quanta are defined only in the asymptotic limits in quantum field theory, which I do not find as quite realistic. If you ask yourself mathematically what's going, that's really an idealization. However, that's not necessarily a bad thing. You can use ideal things to structure the world. They're certainly not robust enough to be identified with interacting particles. So usually you've got your basic particles. When you study particle physics, the actual empirical side of applying quantum field theory, you set up some states where you have a certain countable number of particles in a particular state of momentum and spin. We know what those particles are for ways that I'll say later. And then you allow these things, you imagine they're going to come together because you think classically, and they're going to have trajectories and they're going to bang into each other, and then you're going to find the products that come out, right? But in the middle, it's very difficult to define quanta in this way. The mathematical mechanisms you need to actually represent the quanta as they are defined are not really well defined during the entire process where the actual physics happens. This is a little bit problematic. So I'm trying to surpass that boundary. That's the main motivation for my work. And I, of course, trying to think in the framework sense and being somebody who's trying to reconsider metaphysics a little bit. So I think it's very important, while still doing metaphysics, to keep your principles in mind and look to those principles to see what you're allowed to do without actually violating basic ideas of quantum theory and relativity, for example. So, again, if you hadn't really thought about any of these things at all, you're a student of physics, for example, and somebody told you, okay, so now we're going to talk about quantum field theory. Okay, and if you're sufficiently deep thinking, you might ask yourself, okay, what is this theory even talking about? If you don't get immediately grabbed by the harmonic oscillator in the first 15 seconds and just lose it all in a blur after that, which I think typically is what happens. But I would like to point out something. that shows the significance of particles in ontology that leads one to actually not just take on this idea of quantum as basically excitations of modes of the field, which is the way usually you structure quantum. Elementary particles are trans-theoretic, and that's a very good thing if you're looking for fundamental ontology. I don't really want to be saying that what the objective nature of the world is something which is given to me by theory, which will change as far as we know. There's an induction you can do looking at the history of any science that has any degree of maturity is when we say, well, you're going to find these revolutions. Okay, you can debate about what, if there's meaning change when that happens, and is there reference change and so on. But I think it's fairly clear if you look at physics of electrons, for example, they were hypothesized in 1838, maybe not certain people were actually aware of that, and they were verified in 1897 in terms of their basic properties. Again, modulo everything is different between classical and quantum physics, but still true. And they appeared in old and new quantum mechanics once the subatomic realm was encountered. Then, of course, that's when the revolution was necessary, and the treatment of these things had to change. The characteristics of these things had to be reconceived. The metaphysics of them had to be rethought. You know, can we really think of these things as being independent and so on? But certainly they did exist. We continue to talk about those very same things even now. So this suggests to me that we should, and I will show some quotations from Stephen Weinberg, who has a quite contentious relationship with philosophy, supporting this idea in a way. But particles are definitely, elementary particles are definitely considered the articulable quantum objects. You say, well, so we need to use quantum mechanics. Why? Well, we're talking about electrons going around a nucleus, or we're talking about some bulk matter which has, you know, some electrons and in it, and some vibrations happening, and that's how we understand what happens with this quantum matter. Okay. Now, how can we make this? How can we have confidence in having this new, highly developed quantum theory, quantum field theory, having a connection with these earlier things? Well, if one goes through the requirement, and this is really key for the existence of quantum field theory in the first place, to bring relativity and quantum theory together, one has to understand and keep matters consistent with these principles, and that's been done in quantum field theory. And so one finds that there are special relativistic invariants of states, of quantum states of quantum, the corresponding quantum, that help us identify, or at least coherently identify, certain invariant quantities with those quantities that were the ones which were attributed to electrons in the first place, which means you have a connection between previous concepts and experimental data and contemporary ones. And so this is where one can really hope to find a handhold in trying to deal with the situation of having some kind of sort of ideal state of the universe, or the part of the universe which are going to be scattering, and then later on, but what happens in the middle, what is the actual physics is going on. So let's look at someone who really does think about philosophical matters, even persons a little bit of a curmudgeon, Stephen Weinberg, who actually thinks about things quite deeply, even though maybe he has certain cultural issues with some people who work on the humanities side. A very clear thinker who's also not too enamored with the mathematics of things. In fact, people ask Weinberg about his feelings about the apparent inconsistency of the way that people do mathematical physics, and he said, well, you know, mathematics itself is not even really consistent if you think deeply enough, so I'm not too concerned about that. I want to know how I can use this mathematics to be able to connect with the world. So, what does Weinberg have to say about theories? And his textbook, Theory of Quantum Fields, is quite quantum field, actually. Quantum theory of fields, right? So his standard textbook that most people have been using in the 21st century as the basis for understanding what conventional quantum field theory is, contains the following statement, and it's actually a historical introduction to the book, by the way, is highly recommended reading, I would say. So what does Weinberg say about the situation? Well, what we know about particles is more certain, more directly derivable from the principles of quantum mechanics and relativity than other things that we talk about. If it turned out that some physical system could not be described by quantum field theory, it would be a sensation. If it turned out that the system did not obey the rules of quantum mechanics and relativity as particles do, it would be a cataclysm. So this is a very interesting thing to find in a textbook on quantum field theory that, well, you know, these fields, maybe we're really not so certain about them as we are about particles, because particles are more connected with fundamental theories, the fundamental principles of, say, principles of mechanics and relativity. Very interesting. And so there are 3 volumes to this book, and the 3rd one talks about strings. So that brings a little consistency into play. He's just leaving it out there to say, oh, the future, I don't know, speculate. Now he claims, and this is a claim which I'm disputing because of what I've learned in my attempt to understand this ontology. He claims the so-called quantum particles of the Standard Model, which is of course why people are interested in quantum field theory anyway, perhaps the most accurate, precise theory of physics ever achieved, or science in general. The elementary particles, like photons and quarks and electrons, quarks are a troublesome case, but anyway, are quanta of the fields, bundles of the field's energy and momentum. That's quite a statement. If you know your metaphysics, bundle theory is not so good. It's a difficult thing to think about, and it's problematic. And he's not really thinking of that deeply when he uses bundles, but he's saying the same phrase, and it has a sort of intention behind it, right? So, okay, I dispute that. And I believe the reason he's saying this is essentially how he's structuring his view, which again is a very standard view of quantum field theory, which is, well, you start out with what are your simplest interesting states of system? What is, you have a harmonic oscillator and you excite that thing, and then you have fields of harmonic oscillators, and that's your field, and then you excite those and you see what happens with those things, and you find that they have energy, and or if you're going to have them moving, they're going to have a corresponding momentum. Okay, and in those states, those single excitation states would be very basic to the way you structure your ability to think about the world as made of parts. And again, this is a different way of doing what Einstein was thinking of doing, which is by his local realism. It's a different thing. You're not bringing in local realism when doing quantum field theory, although you want locality, you want things to be causal. So just a quick look at this, the way this is done from a mathematical point of view. And this is again a sort of, when you're thinking about the procedure of experimental metaphysics, you always have to see how the mathematics is helping you to structure your thinking and make things very explicit. So if you think about, again, how Weinberg and most people would think about doing these things, you really want to achieve this idea of excitations and the study of excitations of fields. And again, for him, quanta are really just excitations. I find reasons to dispute that and lean more towards the relativity than the quantum. But the idea is that you can build out the Fock space, which would, if you would properly have the symmetry imposed already on the particles that you're going to introduce as the excitations of various numbers for various modes of your field. So Fock space is what you look at, and you basically have a certain number of momentum things, particles, excitations, which are having a certain momentum and a certain spin. And those are various ones that are available, and all the possible excitations you could have would be fitting into your Fock space. If you wanted to think about the particle content of the theory. And again, these particles are just excitations from this perspective. Alternatively, if you really take very seriously that quantum field theory is about fields, then you'd like to have something like is your standard thing in quantum mechanics. You'd like to have something and we'd like to quantize it. And when you observe it, you'd like to be able to observe it. If you go back to Goyal, it's something you'd like to have meet your understanding of what those concepts you've been using are, like momentum, position, and so on. So it was something like it should be a classical correspondent under the right circumstances. If you try to find the closest thing to that, one looks to the operator field in quantum field theory. And then in order to do that properly, you have to have a sort of vacuum state, and you have to have a certain number of particles and antiparticles, which correspond to positive and negative frequencies of your field modes. However, it's been shown in the more mathematical side of the philosophy of physics that there's a sort of unitary equivalence between these two descriptions, and any problem you're going to have with thinking about particles in quanta when they start to interact, when the structures are available, that's going to bleed over into your ability to think about the fields as well. And this is highly problematic because the assumption has always been, no, this is a theory of fields. We have excitations, we have some energies. Okay, so we can't describe them when they're interacting. But if you can't describe the fields when they're interacting, you've got an issue. And that's what's driving me to my current perspective of trying to do a little bit better. So I'm a big fan of Schwinger, and I'm not going to talk about Schwinger's source theory because it's quite a distinct and unusual thing. But people who are interested in phenomenology may or may not be aware that the use of the term phenomenology in physics actually finds its its source in Stringer, who was the chairman of the physics department at Harvard at the time, had a big impact on even how the archive has a phenomenology section. So this is very interesting. But Stringer really wanted to understand physical processes. He didn't like this idea of, oh, we've got these particles, these quanta, which are just excitations of modes, and then something happens, we don't know, and then we find the particles coming out. So we prepare particles and we measure particles. Right? But what's happening in between? Okay, so obviously people are doing physics, they're doing physics, they want to be able to make predictions and say, yes, I was successful, yes, I've done this, yes, I've done that, by going to the LHC, which costs billions of dollars to maintain and operate. There's a reason for this. So how does this business work? Well, basically you want to find, at the basic level, you want to save the appearances of things. You want to be able to say, well, this is what's observed, so just by theory, at least tell me that yes, what's observed is consistent with the mathematics that I've been using to structure my theory. So you look for the transition probabilities for starting with some setup and then finding some outcome of your scattering. Right? And so this is usually done by S-Matrix procedures, which is mathematics, which was developed by a sub-field of quantum field theory, which was very minimalistic, but it had ultimately issues and was given up. But the idea of using the S-Matrix to find these transition probabilities is quite strong. And the reason for that is it allows one to use perturbation theory, which is a very powerful technique for making predictions, which is something, by the way, that the algebraic approach to quantum field theory has problems doing at all. You make your predictions using a predictive theory theoretical way of calculating those probabilities. You'd like to use your perturbation theory to get accurate predictions, and these are, again, amongst the most accurate predictions that are found in science at all. So this does work. However, again, what's the understanding? One finds that you do not, under circumstances of interaction, that nice mathematical structure I showed you before fails because you can't distinguish particles from antiparticles. There are issues about how causal things are if you try to define your quanta during the circumstances. You can have things bleeding out of the light cone. It's not a good situation. Okay, so what does one do in order to get away from the situation that interactions are just a black box? If you agree with Weinberg, despite everything, that actually particles are the things which are most closely connected. Okay, so what can one do? What do people actually do in practice? So there's a very nice book by David Kaiser on diagrammatics and quantum field theory, a very nice study in the history of quantum field theory and the use of Feynman diagrams and other diagrams that were used by other people, especially in Japan, figure out how to do these calculations. And the most important thing is doing the proper accounting while you're doing this procedure. And many people did entire PhDs on just doing one calculation in this stuff. So it's really very difficult to do. But there's certain rules for how you should be able to, there are constraints that come into what's possible. So what's quantum mechanics it's really about? I've got some starting state. What are the possible ways of reaching the ending state? You calculate the likelihoods for those things by having the probability amplitudes and squaring them. That gives you your probabilities that you use. And then, of course, you have conservation laws that you'd like to apply and so on. So the rules for the diagrammatics that are used in practice for calculating most calculations involve certain assumptions. And the way you actually do these calculations is that you think about particles diagrammatically having some interaction with each other. And there's an attempt to structure these things in a very, very general way as being within space and time, but these are topological diagrams because when you do the summations, you have to actually sum over the whole universe or all the momentum which are available. So it's a very abstract thing. And the problem is that if you start saying, well, the diagram is actually going to help me because that's actually what happens in practice amongst physicists. As soon as you start saying this is a space-time diagram, you have real problems because it's not a space-time diagram. What it does tell you is, though, there are local interactions that happen between particles, between quanta, between things which you would like to think of as excitations. So you'd like to use these rules to see how you can actually get something out of these diagrams as a kind of guide while not violating relativity or quantum theory or theoretical principles. So if you actually look at the mathematics of what's going on here, and ask yourself, again, now if I want to have particles interacting, right, and I want to talk about fields, and I have difficulty with using clock space in the intermediate case, I have difficulties actually also having particles at all, even if I'm allowed to use fields during the interaction. You are allowed to use fields. You do use fields in these calculations, but you have to use a very special form of field if you think that they actually can love define. But you can do that. But what you find is the mass that's attributed to the field takes on different values from the mass that's attributed to the particles in the ideal case. And if you think about the closest thing to the thing on Z, the thing in itself, the actual particle, when it's isolated, it should be showing its properties, not when it's involved in a complex situation. So this suggests that what's happening at the field level, although essential because that's when the way the theory works and actually the necessary existence of a state where there are no particles at all, you still like to think about the field relationship to particle in a way that the fields are involved as well. So you have fields which have actually the possibility of having a mass attributed to those elements or contributions to the overall field state, the ones that correspond to really what you might like to think of as propagation, having masses which are not the ones you attribute to particles. This is called going off shell. There's quite a lot of distinction and confusion amongst even graduate students who specialize in quantum field theory and what happens when you go off that shell. What happens is the mass that you give to a free particle that defines that particle and defines it in other ways, which I'll get to in a second, it's not the same as the field. Okay, so you've got this curious situation. Field is essentially treated in practice as the fundamental thing, mathematically speaking. You can actually define it in a well-defined way, but it no longer connects to the thing which is most well connected to the principles, which is relativity and basic quantum principles. So this, in my view, turns out to be highly significant, and this is what suggests a supervenience relationship between particles and fields. I'll argue that you can actually suggest that both exist, but the relationship with them is one of supervenience, just in a certain way that people have minds and mental states, even though they're physical bodies. Although again, this analogy, I don't want to push it too far, it's just a matter of where supervenience has been used so far, which is mostly false in mind. Okay, so of course you might think, well, I can just make up any sort of particles I want. The theory, if I'm going to say that I'm going to define the particles the way that they've always been defined. For example, it's one noted here, and I'll read this to give a kind of reference, but basically, what's the mass, what's the spin and charge of the particle? You can't just choose any values you want. Actually, it's one of the successes of quantum field theory that you can actually pick out, amongst other things, like, for example, that you have bosons and fermions, but you can actually pick out which masses and spins can actually be allowed by principles of relativity theory. So let me just read this quote. The main invariants that one finds are charge mass, and in that case, actually rest mass, spin. And when we're able to determine these quantities, we decide they have to do with a definite particle. Well, it sounds a little bit like the physicist's realism, right? Okay. But we're justified that invariance is really. But this is a trans-theoretical definition, which is a good thing when you're trying to realize that theories are changing. So if you stick with your framework, don't violate relativity and quantum theory principles without having the critical basis to do that. But try to think about trans-theoretical definitions of things. If you just think about particles as having masses, charges, and spins, and that's their defining characteristic, you might be able to do better by going back and returning to these Feynman diagrams and trying to make sense of them consistently. Now, there are huge arguments that people have against this kind of procedure because there are certain characteristics mathematically of these perturbative expansions which suggest interpreting them realistically is problematic. But I would argue that the Feynman rules actually give you a very strong basis for that. And if you stick to those rules, rather than the pictures, you will not go into the consistency. Okay, so it's really a question of having these properties, mass, spin, and you can also have charges, and this has to do with other things which I don't have time to talk about. For example, electrical charge. As being calm presences. What do I mean by that? When I make an observation, I find mass and spin and charge together in ways that are associated and have always been associated with the elementary particles that we have observed. So when you have property compresences, you're starting to give structure to something. So for me, this is the basic starting point of trying to think about what's the fundamental ontology of field theory. Work to these compresences, and then try to relate them to the formalism and remain consistent about what you say about them. You can't just choose any sets of properties, and actually the nice thing is that what you observe in the real world actually connects with the quantum theoretical treatments of these things from a relativistic point of view. Okay, so they're well defined during interactions, these things, even when virtual, which is again a contentious thing. People use virtual particles to think, but other people don't like them. So the value here is you're going beyond saving the appearances of things. This is really to be a realist, right? It's not just enough to say that I'm thinking in a way which is consistent with what I observe, but it actually can go beyond that to be thinking of things realistically, and depending on how you feel about realism. Like say the forms are real, but you're playing this and still be a realist. So I don't particularly a priori constraints on that. Okay, but the main thing is it allows you to explain processes as having some characteristics before they're detected. Now, of course, there's always the quantum measurement problem, right? And that's going to remain a problem in quantum field theory, but nonetheless, after processes have occurred, you do have the ability to connect the initial states and the final states together with the diagrammatics as a basis for thinking about how interactions can happen, therefore actual physics in between preparation and conversion experiments. So what is it that determines this structure? Just to show you that this isn't just some easily said thing, it actually has a very strong basis. I believe a paper written, which I believe is in 1939, basically found that if you impose the Poincare group structure invariance on top of quantum Hilbert spaces, such as you find in quantum field theory for the individual excitations, that there are certain invariance, mathematical invariance Casimir operators, which correspond to masses and combinations of masses and spins for which you can get spins. So you have this things which correspond to what are seen in presences of mass and spin, and if you bring in other groups, which is more complicated, this is various charges. So you actually do have a relativistic basis if you're going to be doing quantum theory for picking out these quantities as those things which are real. And if you go back to the oldest metaphysics that has anything to do with observations in science, it was the question of the motion of the planets, right? What's eternal? What's perfect? The circle. We're going to use circles to describe what we see in the heavens. Right? A similar sort of thing, but very, very much modern. Okay, so one finds various things like conservation laws for the properties, energy and momentum and angular momentum, and so on, that allow you to also constrain what you'd expect to see and to be consistent with the experiment. So, to get to the basic question of my answer to what's happening with particles and fields in quantum field theory, is that the particles supervene on the fields, and what does it supervene as human? Because I've used that phrase probably 4 times, but I haven't really said what it means, right? So the idea of supervenience, if something supervenes on something, is a bit like reduction, but without reduction. So I suppose that most people understand the notion of an ontological reduction. So, for example, so this gets a bit complicated, but the idea, if you have an ontological reduction, is that you think that something exists which you can explain the fact that you don't need to refer to that particular concept in order to do a proper explanation of what's going on. So if I could reduce, for example, if I could reduce mental states to neurological states, there wouldn't be any need to talk about mental states at all. It would be redundant. I could talk about them, but there would be manners of talking about the nervous states. So it's a similar thing that I'm arguing in the case supervenes here for particles and fields, which is you cannot just think of particles as being a manner of speaking about behavior of exciting quantum fields. But actually, you need the particles to be able to have any kind of sense of the interactions that are taking place between the initial state and the final state. In other words, actually allows you to start to do physics about quantum field theory, not just having some stagnant ontology. And again, why would you need, if you do so well in all the things that I've been telling you about, just tracing the behavior of these invariant quantities through observations, why would you need to have fields? Well, beyond the mathematical things that one is allowed to do in calculations of scattering matrix, fields also account for the no particle state. What does it mean to have a no particle state, which is essentially part of your mathematics? Well, there's at least a vacuum. So if you've got a vacuum, you might as well have a field because it's going to have all the properties of all the ontological aspects, I would say, that are essential aspects for the field. Okay, so particles depend on the field and the properties which are correlated as one sees. So this is why this whole picture is consistent. But since the mass term that you find in the field description is not a fixed one, then you have difficulty saying that I've got this particle with this mass actually in the intermediate state. It's very odd to say I have a particle, this ideal thing, it's really there, but it's not there at all. And I get some end of the operation and it's there again. So it wasn't involved in physics at all, but it was real. So it's a little bit of, a bit like critiquing the forms of Plato. So I think I'll just stop there since I'm running short on time, as I tend to do. So thank you very much for your attention.
Please do use the microphones. Let me unmute this on personal level. Can we use yours? I don't know. Yes, mine is working. Great.
Thank you very much. That was very intriguing. And so I'll be very short, but I think I would like to suggest something which I think is consistent with everything you said, but
What's exciting?
in the completely opposite direction.
Even worse.
Yes. Namely, maybe we should think, so the overall direction is reductionism, ontological reductionism, to fields. But of course, you don't have to reduce.
This is what you're suggesting.
Yes, so of course, you don't have to reduce something that doesn't exist. So particles, I think, and I think you're saying particles supervene on fields. I would say rather that particles are part of the story. Or actually, they are part of our mental state. They are the story we tell in some circumstances in which we can tell a story, make sense of whatever happens, especially in these in states and out states, but not in the interaction. So I think that, of course, we start with what we experience, which are part of it. But once you have the theory, and you want to make sense of your experience, this is what we want to do, basically in physics, I think, ultimately. So I think you can tell exactly the same story that you tell, but go in this opposite direction, saying yes, but the ontology is the fields.
Well, so
And the particles are just
right. So this is actually, I would say, quite a standard and thoughtful way of dealing with things. And I think that this is really what Weinberg is doing. But there are a couple of things that are an issue, which is first of all the discreteness that one finds, these compresses, these comings, and whatever. And you might get to argue, well, I can tell a good story with fields. I don't really need. The fields can somehow be discrete fields. It sounds odd, but that's the way they are. That's, I think, the way that people usually respond. But there is this problem of the non-observability of fields. And also this technical mathematical problem that I referred to, which is that you have trouble actually, when the interacting case, structuring the fields in such a way that it has anything to do with what's happening with the Feynman diagrams and so on. And I'm perfectly open, and I don't think it's wrong to say that those are just figments of calculations that one shouldn't think. But then, you've lost a lot of what one wants to do in physics, the intuitive part of this. So I think we're on the same wavelength. It's just a question of priorities. Let's say.
So we have 5 more minutes for questions. Guido, please.
One question and one analogy I'd like to suggest.
I think it's on.
Is that working now? Should be. No. Into the side, okay. Well, hopefully bars.
It's a couple answers.
I was, could you clarify how you see the sort of reality of virtual particles insofar as, the various diagrams correspond only to terms in the perturbation expansion. So, there's some kind of superposition of different particles or something like that, and how that fits with your view there, and just suggesting a sort of an analogy, with the kind of historical analogy, with Max Born's treatment of collisions in 1926. Also there, he's doing a sort of an asymptotic treatment. You've got sort of stationary states, plane waves, coming in, or stationary states of the atom, at minus infinity and at plus infinity, and the collision is some unvisualizable, thing, which might be conceptualized in terms of quantum jumps. So, for him, what's visualizable, are those particles with stationary states, but they are only well defined at minus infinity and plus infinity, and then there's the interaction which is not.
So I'm not too aware of that particular paper, which of course we'll talk about later when I was look up. But the general question of the relationship between the what's happening with these virtual particles and the expansion, and then given this modular various concerns that people have about interpreting them, and again, for sure they're not space-time diagrams, but in any specific sense. But the matter of fact of how the terms of the expansions arise is actually having to do with the topology of connection between these things. And so every time you have an internal line, this is the very definition of a virtual particle. And anything that you're actually going to have any empirical connection with will be ultimately something which doesn't propagate forever. So in that sense, will also be virtual. This is a kind of consistency problem with people who like to make a distinction between free particles and virtual particles, because to me, this distinction is artificial. In fact, it's even more introduced if you think that these diagrams have no connection with reality. So the accounting has to do with, basically what is the power in the coupling that you find, and that will tell you how many particles are in. And there's not much spatial temporal structure to any of this, so that's still lacking. I hope that helps a bit.
We had a question somewhere here, and I didn't quite remember where it was, but you had a question? Sure. Yes, so we have time for one last for the comment. And don't worry, if there isn't enough time for your question, we have the discussion panel, so we can figure stuff out later.
So I'll be very quick because it will have break. If one is not a realist like you, can one have a different understanding, for instance, of final diagrams than you do?
Oh, absolutely.
Because if one is not a realist, one would not object to the iconic character of the diagram as a representation in space-time. It doesn't have to represent truly real stuff. While keeping on the symbolic aspect of the diagram, clearly it has a symbolic role. It's fundamental, which allows for the calculation of probabilities. So how much of all this talk depends on the realism commitment?
I think the whole program, the whole basis has to do with I'm not a realist. I would not be concerned with this problem at all. But I went just point out one historical fact, which is that Feynman actually vacillated in an extreme way with regard to this question. He was asked, I think within the period of 2 years, what was the nature of these diagrams, or at least what he was thinking. The first one, I was thinking very physically, and the second was, it's just mathematics. And he said the two opposite things in two different periods. If most people would say, oh yeah, they're just mathematics, that's what he was saying, and you find Freeman Dyson saying, Dick was just thinking about the physics, he didn't care about the mathematics. That's why people didn't respect the diagrams when they first came out. Because he was a very young person, almost postdoc or assistant professor when he first introduced his diagrams. Nobody understood them. Nobody liked them. Because of the-
I mean, a follow-up to that is that one can tell to be a realist and not necessarily then be committed to it all being mathematics. I mean, I don't see that as a
No,
necessary
I'm saying,
corollary.
no, but I'm saying if you.
And I think Feynman was not a realist. I don't think he was a realist. But certainly he was concerned.
We can talk
Well, we can talk about that. But certainly he was, even on my reading, where he's not a realist, he was certainly concerned with physics. I don't see why you being a pragmatist, for instance, requires you to read Feynman diagrams as a piece of mathematics only.
Yeah, and you can be also a solipsist, that's also fine. It's perfectly mathematical, philosophically consistent with a solipsist. And I actually wouldn't object to that at all, right? Or being ethically just an egoist, I mean, that's also very, very viable. The question is, when one does physics, the implicit thing is it's realism. But I'm not some sort of imperialist when it comes to ideas.
Thank you.
Right, let's give our speaker a big round of applause.